Okay, so this is the Zoom meeting for Physics 232C. We've finished the first exam, and now we're going on to chapter 19, which is on electromagnetic induction. So you've probably already read the chapter. It's important to read the chapter and take notes. These are some of the notes you should have. The notes you take should mainly be equations. So here are some of the notes that you should have. Chapter 19 is pretty long. It has a lot of different parts, but it starts with Faraday's law, which is a fundamental discovery going back to 1831 by the great Michael Faraday, that when a magnetic field changes, there must be an associated electric field. Or we could write it in terms of the electromagnetic force, the EMF, around a circuit. So the EMF around a circuit is the rate of change of the magnetic flux through the surface. And you need to know the definition of flux. Flux is field times area. So when the magnetic field is changing in time, the rate of change of the flux through a surface is equal to the electromotive force around the boundary of the surface. And remember, electromotive force produces current. So this presents a new way to produce electric currents. You don't need a battery. You just need a way to change a magnetic field. So that was the great discovery, a laboratory fact. And that's the way we make electricity today. So when you plug something into a wall socket, you're making use of Faraday's law in an electric power plant someplace. That's how we get electricity. So our society depends very much on Faraday's law of electromagnetic induction. There's a section called motional EMF, which shows that when an electromotive force when a conductor moves through a magnetic field, there's an electromotive force around the conductor. And again, that will drive a current. But the current is sort of a secondary effect. It's really the electric field, which is the primary effect. And then the electric field creates current. Many technologies depend on electromagnetic induction. And so there's a section on technologies. In particular, the electric generator, a rotating conducting coil in a magnetic field, produces an alternating electromotive force. And if that's then connected to a circuit, there'll be an alternating current in the circuit. Transformers are an important part of the electric grid. Throughout the United States, or throughout the area around cities, there are transformers which help to control the electric grid. The voltage in your wall socket ultimately comes from some transformer. The transformer works on the basis of electromagnetic induction. Now, there's another part of chapter 19. This part is, the earlier part is on fields, the electric field, the magnetic field. The remainder is on circuits, alternating current circuits, and in particular, circuits with inductance. So there's a definition of inductors, that's one section, which defines the self-inductance L. And you should understand these equations. This is the definition of L. This is how current changing, the rate of change in time of a current around an inductor times the inductance gives the voltage difference across the inductor. So this is a topic for electric circuits, and in particular, circuits where the current changes in time, primarily alternating current circuits. So there's a whole section on AC circuits. How does a changing voltage imply a changing current? And it's a little more complicated than DC currents. DC currents we studied before. DC currents, we have Ohm's law, it's very simple. The voltage is the current times the resistance. AC circuits are different. For an AC current, you have both the voltage and the current will be alternating in time. There's a phase shift. And the relation between the strength or the amplitude of oscillation of the voltage and the current is given by something that looks a bit like Ohm's law. V0 is I0 times a constant, only the constant is not the resistance. The constant is what's called the impedance. So actually this last section on AC circuits, that's a long section, and you'll be using that in a lot of the homework problems. Let's go over a few problems. I won't go over the solutions today. I'll go over the solutions at the Zoom meeting next week. So this Zoom meeting today is really just to get you started on chapter 19. We'll have another Zoom meeting on chapter 19, which will be to go over solving problems. But that'll be for a week from today. But let's just see what kind of things come about. Here's an example of a problem which is in the homework assignment, which is due, I guess it's a week from Wednesday. It's not due this week, it's due next week. A circular coil of wire has N turns, radius A, resistance R. A magnetic field, perpendicular coil, is changing in time at a rate delta B over delta T. Remember, that just means the change in B over the change in T. B is field, T is time. So it's the Tesla per second in terms of units. Number of Tesla divided by number of seconds, Teslas per second. So that's the rate of change of the magnetic field. That's a perfect example of electromagnetic induction. There's a change in flux through this coil that produces an EMF around the coil. There'll be a current. Find the induced current. And some parameters are given. So we always do these problems in the same way. We draw a picture. So here's the picture. And then we write down the necessary equations. So we'll know what we're using. EMF is, actually it's the negative of the rate of change of the flux. The negative sign controls the direction of the current. Is the current clockwise or counterclockwise? If the magnetic field points in this direction, upward, and it's increasing, then the rate of change of the flux would be positive, the EMF would be negative. That corresponds to counterclockwise current. You have to use the right-hand rule to determine the direction of the current or the direction of the induced electric field. In this case, the flux is the magnetic field times the area, but also times the number of turns of wire, because each turn of wire has a changing flux. And then to answer the question, what's the current? Well, we just use Ohm's law. It's the EMF divided by the resistance of the wire. Here's another problem from the problem set 5. An AC power supply is connected to a resistor. The root mean square electromotive force is VRMS. So there's an alternating voltage here. Unlike a battery where the two terminals have a constant voltage difference, in a AC power supply, the voltage difference is alternating. Sometimes this is the positive terminal and this is the negative terminal. Half a cycle later, this is the negative terminal, this is the positive terminal. So it switches back and forth from positive to negative. That's an alternating voltage difference. And that produces an alternating current around this circuit. You're supposed to calculate, well, what you're given is the root mean square voltage. The average voltage is 0 because it's alternating between plus and minus, plus, minus, plus, minus, plus, minus. You take the average as just 0. But if you square it and take the average of that and take the square root, that's the RMS. And it's 110 volts, like you would have in a wall socket. It's giving you the maximum current. It's giving you the angular frequency, omega. Omega is the angular frequency, radians per second. Omega divided by 2 pi is the frequency. That would be cycles per second. And you have to calculate the RMS current, the resistance, because you're given information about the current, you can calculate the resistance, and then the average power. You remember from previous chapter, power in a resistor is I squared R. Well, that's fine for direct current, but what about alternating current? For alternating current, we have average power is the root mean square current times R. You calculate the average of the power over time. You calculate the average of I squared, that's I RMS squared. Everybody has an electric generator that they take around with them, carry around with them. It's the alternator in your car. Well, you're too young to have a car, but your parents probably have a car. So every car has an alternator. The alternator goes bad, car won't run. So I suppose every car owner has experienced that. So this is an example of an electric generator. And there's a chapter, there's a section, a subsection in the chapter about electric generators. The alternator charges the battery. It has to keep the battery charged to 12 volts. If the alternator goes bad, your battery will eventually run down and you don't have any electricity in your car. Now it suggests that the alternator coil has diameter D, spins at 1,000 revolutions per minute in a magnetic field B. So this is a typical example of an electric generator. How many turns of wire are required to produce a peak voltage of V0? I guess V0 is given here. 14 volts. So as with all problems, we start by drawing a picture. Here's a picture of a coil of wire which is rotating around some axis, not really an axle, I really should say some axis of rotation. So there's some axis of rotation, and as the coil rotates in the magnetic field, the amount of flux through the coil alternates between positive and negative. And this, it's going to rotate. So this side's going to come up, this side's going to go back. It'll rotate around like this, I guess. The magnetic field will be alternating. Well, the magnetic field is constant, but the flux of the coil is alternating because the coil is rotating around within that magnetic field. And the equation you need is that the electromotive force is NBA times omega, where omega is the angular frequency of rotation. So they give you the revolution frequency here in revolutions per minute. You need to convert that into radians per second. So the unit of omega is radians per second. And you'll have to convert revolutions per minute into radians per second. So one revolution is, so this would be 1340 revolutions. One revolution is 2 pi radians. 2 pi radians divided by a minute. Well, a minute is 60 seconds. Now, is this electromotive force the maximum electromotive force, or is this the RMS electromotive force? Actually, this equation is the RMS force. What you're supposed to figure out is the peak voltage. So you want to convert from RMS to maximum. Opening a switch in a highly inductive circuit can be dangerous. To see why, consider a 6-volt battery. So here's the 6 volts. Supplying current to an electromagnet. So here's an electromagnet that has a large self-inductance. So there'll be, in this case, a direct current I and a constant magnetic field, as long as the switch is closed. But when the switch is opened, there can't be any more current, because the current can only flow in a closed loop. So with the switch closed, you have a large magnetic field and correspondingly a large magnetic energy inside the solenoid. When you open the circuit, the current stops. Where'd all that energy go? All that energy has to go somewhere. And the answer is it'll make a spark here, which is a bit dangerous. So you calculate the voltage difference between the two points on the switch. You'll find that's very large. That's a dangerous thing. Here's an AC circuit with a plug, plugs into the wall. So here's the wall and a resistance. The American standard is the voltage is 110 volts. That's the RMS alternating voltage. 60 hertz, that's the American standard. That's the RMS voltage. The first question is, what's the maximum voltage? So here you want Vmax. Vmax is just the square root of 2 times the RMS voltage. Part B is what's the RMS current? So that's IRMS. C is the maximum current, so that's Imax. Again, the difference between the maximum or the peak value and the root mean square value is just a square root of 2. D is the power, maximum power. E is the average power. You know, as the current here, there'll be a current here which is alternating. As the current alternates, remember, power is I squared R. So as I alternates between +1, plus I0 and minus I0, between plus Imax and minus Imax, I squared alternates between 0 and Imax squared. And the average will just be 1/2 IRMS squared. No, the average will be the square of IRMS. So, you know, we draw a picture. Here's the picture. And then we write down the equations. Here are the equations. And then you pick up your calculator and calculate the various quantities. Here's another AC circuit. Wait a minute, isn't that the one I just did? That's the one I just did. Okay, I already did that one. Maybe that's the end. We did this one. This one's just the same. This one's just the same. So I guess we're finished now for the evening. So those are the problems that you'll be doing. They're due next week. But those are the kinds of problems you'll need to understand. And it really boils down to knowing how to apply these various equations that you have written down in your physics notebook for a pretty wide range of examples. But chapter 19 is rather long, so we give you 2 weeks to work on chapter 19. And we'll have another Zoom meeting a week from today where we'll go over these problems again, but show some of the calculations. So now I'll end the recording.